Hello, and welcome to the OpenBrIM Platform. In our previous video, we learned how to develop a substructure model using the OpenBrIM Platform. In this video, we will demonstrate how to create a staged construction model. Let us begin. Staged construction analysis is a critical analytical capability available within OpenBrIM. It is designed to simulate and evaluate the structural behavior of bridges throughout the various phases of construction. This analysis enables engineers to assess how different construction stages affect the bridge's overall performance, stability, and safety. To perform a staged construction analysis effectively, it is important to clearly define each phase of the construction process, including the sequence of activities and the specific conditions associated with each stage. Once the construction stages have been established, the relevant bridge components must be assigned to either construction or deconstruction activities within each stage. This ensures that the analysis accurately represents the contribution of each structural element to the bridge's integrity throughout the construction sequence. By utilizing staged construction analysis, engineers can identify potential structural issues early in the construction process, optimize design and construction strategies, and enhance the overall safety, reliability, and durability of the bridge. First, we click on the Construction Stage object located under the Construction category in the tree view. After each construction stage, the finite element analysis produces results that can be utilized to ensure structural compliance with codes. To create the stages correctly, users must understand the underlying logic. At the start of the staged construction analysis, all structural elements are in an unconstructed state. Constructing a typical steel bridge requires defining at least 4 stages. First, pier or foundation construction. Second, girder and bracing construction. Third, application of deck loads on non-composite girders. And finally, deck stiffness gain. Introducing deck pouring stages will require additional stages for non-composite and composite stages. For example, if the deck is poured in 3 stages, 6 stages will be necessary, 3 for deck load application on girders, and 3 for deck stiffness gain stages. For permanent loads, such as wearing surface loads and barriers, 2 extra stages may be required. Additional stages will be necessary for each transient load, such as wind loads, braking loads, live loads, and temperature loads. A simple way to think about staged construction is this. Each time a new structural condition or load type is introduced, a new construction stage should be created. For users who are new to staged construction analysis, introducing a new load case can generally be understood as introducing a new stage. This makes it easier to track the structural response step by step and evaluate the bridge at each point in the construction sequence. We click the name parameter and define the first stage as Substructure stage. The continuity of stages is maintained using the prior stage parameter, which instructs the software on which stage to analyze next. For the first stage, the prior stage will be none. As additional information, if users wish to apply temporary loads, such as wind or live load, they can select the final permanent load stage as the prior stage for all transient loads. We leave the construction method parameter at its default for this stage. The construction method parameter offers 3 options: none, equal, and match. Usually, node coordinates are utilized as user inputs without any modification. However, certain scenarios require adjustments to the node locations based on prior stage deflections. For example, during the construction of girders and the application of deck load, girder nodes experience displacement while deck nodes do not. In construction site scenarios, the deck formwork also undergoes deflection due to girder displacement. To address this, the node coordinates of the deck must be adjusted based on girder displacements. The equal parameter modifies the initial node coordinates of the deck shell elements by applying the top node displacements of the girder to the closest nodes. For a typical steel 1 girder bridge, pier construction, steel 1 girder construction, load application on deck, and transient load stages will typically be defined with the none parameter. However, the stage that represents the deck construction, the deck hardened stage, should be defined with the equal parameter. The match cast technique is typically not used in the construction of steel 1 girder bridges and is generally applicable to segmental bridges. Now we click the three-dot icon button in the load type parameter and select it. Selecting the appropriate load types, such as dead load, wearing surface load, and wind load for each stage is crucial. And different load types should not be combined in a single stage. In the following steps, users must combine the results of each stage based on their load type using AASHTO load factors before code checks. Combining results becomes more challenging if more than one load type is applied in one stage, or if load types are not selected correctly. In summary, the load type parameter allows users to filter results according to load type, providing a way to organize and analyze results more effectively. In the interface that opens, we select Dead for this stage. We leave the active parameter as Yes. This determines whether this construction stage is active and included in the analysis. When set to No, the stage will be excluded from the analysis. We click on the time-dependent category. Typically, in a steel 1 girder design project, time-dependent staged construction analysis is not necessary. However, if the bridge owner requests CEB-FIP 1990 creep and shrinkage computations for the substructure, or if post-tension tendons are employed for the pier cap or pier columns, time-dependent analysis can be conducted. We leave the parameters in this category as default. In upcoming videos, this section will be examined in detail in the video covering the definition of the precast 1 girder model. We click on the nonlinear category. This section is where adjustments are made when nonlinear analysis is required in the model. For example, soil structure analysis or pushover analysis. We leave the parameters as default for this model. If you would like to examine the parameters in detail, you can use the documentation whose link is shared below. We click on the AASHTO category. OpenBrIM already computes stresses during the design phase based on long-term and short-term section properties. However, if an analysis beyond the design phase is required, with modified E for short-term and long-term loads, this category can be used. We also leave the parameters in this category as default for the substructure stage. We click on the stage category again. We click the name parameter and set the name as girder stage. We click the three-dot icon button in the prior stage parameter and select substructure stage. For other stages, we copy and paste the data from the Excel link provided in the video description. To make long-term and short-term definitions, we will first define a material. The material we define is used to override the long and short-term properties. We click on the material object under the Properties category. We click the three-dot icon button in the name parameter, then select Import Material. In the interface that opens, we select Concrete Material for Database, US AASHTO for Category, and finally, 4 kips per square inch for Asset. Then we click the Import button. The material has been created. Then we click the name parameter and set the name as 4 kips per square inch for Deck. We return to the construction stage object. We click on the AASHTO category. For transient loads assumed to be applied to the short-term composite section, the concrete deck area shall be transformed by using the short-term modular ratio. For permanent loads assumed applied to the long-term composite section, the concrete deck area shall be transformed by using the long-term modular ratio. If the long-term option is selected, this parameter will override the modulus of elasticity values of the selected material. The long-term modulus of elasticity is computed by dividing the selected deck material's modulus of elasticity by 3. As per AASHTO standards, the deck's modulus of elasticity and section modulus must be adjusted for design purposes when calculating stresses. Starting from the stage in which the deck gains stiffness, we set the composite section parameter of the deck stages, barrier, and future wearing stages to long-term. We also set the newly defined material to these stages. Starting from the live load stage, we select short-term for the direct load stages as well. Similarly, we set the new material for these stages. We have completed the definitions of the construction stages. Now let us determine in which stages the objects in our model will be created. We click on the Pier Cap or Bent Construction object under the Substructure Construction category in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Substructure stage and click OK. Then we click the three-dot icon button in the Pier Caps or Bents parameter and select Pick. We select Pier Cap 1 and Pier Cap 2 from the screen and click Done. We leave the self-weight factor parameter as default. We also leave the Pier Cap Construction method parameter as default. This parameter offers the user three options: controls how the pier cap or bent contributes to the structure state created by this construction stage. Select weight only to apply the self-weight scaled by the self-weight factor without adding the pier cap stiffness to the model. Useful when the element carries load but is not yet structurally engaged. Select stiffness only to activate the pier cap stiffness without applying its self-weight. For instance, when the weight has already been accounted for in an earlier stage. Select weight and stiffness to apply both the scaled self-weight and the stiffness, which is the typical choice for a fully constructed pier cap. We have completed the Pier Cap Construction definition. We click on the Pier Column Construction object in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Substructure stage and click OK. Then we click the three-dot icon button in the Columns parameter and select Pick. We select all pier columns in the model from the screen and click Done. We leave the self-weight factor parameter as default. We have completed the Pier Column Construction definition. We click on the Foundation Construction object in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Substructure stage and click OK. Then we click the three-dot icon button in the Foundation parameter and select Pick. We select Footing 1 and Footing 2 from the screen and click Done. We leave the self-weight factor parameter as default. We have completed the Foundation Construction definition. We click on the Pile Construction object in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Substructure stage and click OK. Here, two different definition methods are offered to the user for pile construction. First, all piles under substructure. Users can conveniently select connected substructure elements instead of individually choosing piles. The library component automatically identifies and constructs the connected piles. The other option is individual piles, which provides the ability to select piles one by one. There is no need to reselect piles under substructures if the All Piles Under Substructure parameter is used. We click the three-dot icon button in the All Piles Under Substructure parameter and select Pick. We select Footing 1 and Footing 2 from the screen and click Done. We have completed our pile construction definition as well. We click the FEA button from the left menu. As can be seen on the screen, the finite element model belonging to the partial definition was created at the determined stage. We click on the Superstructure Construction category in the tree view. In this section of the workflow, users can define the sequence of construction for superstructure elements. Each element is represented as a separate object, each having different parameters that need to be defined. We click on the Bearing Construction object under this category. Bearings should be constructed in the same stage as the related girders. If they are constructed prior to the girder construction stage, instability may occur, leading to a failed finite element analysis. Conversely, if bearings are constructed after the girders, it may result in inaccurate FEA results. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select Girder Stage and click OK. We click the three-dot icon button in the Insertion Points parameter and select Pick. We select the insertion points in our model from the screen. Now let us define the stage for girders. Two construction options are available in the workflow for girders. You can construct your girders in a single stage by selecting the complete option in the model, or you can select the partial option to construct the girders partially. In the typical design process of a steel I-girder bridge, the girders and cross frames are constructed in a single stage. For this reason, we will construct our girders in a single stage in our model. Before proceeding to this stage, we click on the girder partial object in the tree view in order to show how the partial option works. During the typical design process of steel I-girder bridges, a detailed analysis of the erection sequence for girders and cross frames is usually not necessary. Engineers who are responsible for girder erection typically conduct this detailed analysis after the design process. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select Girder Stage and click OK. We click the three-dot icon button in the girders parameter and select Pick. We select two girders from the screen and click Done. We set the girder start station to 100 feet and the girder end station to 200 feet. Then we click the three-dot icon button in the cross frames parameter and select Pick. We select two cross frames from the screen. Now, to continue with the model, we remove the definition we made and proceed with the girder complete definition. We click the three-dot icon button in any parameter and select Delete Row. In the interface that opens, we select Confirm. We click on the girder complete object in the tree view. We click the three-dot icon button in the stage parameter and select Select. During this stage, finite elements for girders and cross frames will be constructed, and their self-weight will be applied concurrently. In the interface that opens, we select Girder Stage and click OK. We click the three-dot icon button in the bridge parameter. All girder and cross frame components of the selected bridge will be constructed at the selected stage. We set the bridge object. If splice load and stiffener or gusset plate load are to be included in the finite element analysis, the three-dot icon button can be clicked in the load parameters and Include can be set. We also leave the girder self-weight parameter as default. The girder self-weight factor is a parameter used to adjust the contribution of a girder's own weight to the overall structural load calculations. This factor allows for the scaling or modification of the girder's self-weight in finite element analysis. We have completed our girder construction definitions. Now we click on Deck Construction in the tree view. Composite deck pouring is a method of constructing a bridge deck where the deck and the girders act together as a single structural unit, which can significantly increase the load carrying capacity of the bridge. In steel tub girder bridges, composite deck pouring is achieved by using a concrete deck that is poured onto the top flanges of the steel girders, which are typically designed with shear connectors such as studs or shear tabs. The composite deck pouring sequence typically involves the following steps. First, preparing the steel girders. The steel girders are fabricated and erected, and the top flanges are prepared with shear connectors, such as studs or shear tabs. Second, placing the formwork. Formwork is placed on top of the girders to create a mold for the concrete deck. Third, placing the reinforcement. Reinforcement, such as steel bars or mesh, is placed within the formwork to provide additional strength to the deck. Fourth, pouring the concrete. Concrete is poured into the formwork and leveled to create a flat surface for the deck. Fifth, finishing the surface. The surface of the concrete is finished with a trowel to create a smooth, even surface. Sixth, curing the concrete. The concrete is left to cure, typically for several days, to gain strength and durability. Finally, applying the wearing surface. A final layer of asphalt or other wearing surface is applied to protect the concrete deck and provide a skid-resistant surface for vehicles. During composite deck pouring, the girders and the concrete deck are designed to work together to carry the load of the bridge. The shear connectors on the top flanges of the girders transfer the load between the girders and the deck, creating a composite structure that is stronger than either component alone. The result is a bridge that can carry heavier loads and has a longer lifespan than a non-composite deck. Prior to the deck pouring stages, it is important to confirm that the substructure elements, such as foundations, piers, pier caps, abutments, and superstructure elements, girders and bracings, have been constructed. In some models, substructure elements may not exist, and fixed supports may be present at the bearing locations. For such models, it is necessary to ensure that girders and bracings have been constructed in the previous stages. It is also crucial to apply the formwork load in the previous stages. In our model, we will define the deck object in 5 stages. For typically sized bridges, the most common placement sequence involves pouring the positive bending moment regions first, followed by the negative moment zones. The positive moment zone pour is typically defined as being between points of dead load contraflexure. After the positive moment zones have sufficiently cured, usually several days, the concrete for the deck in the negative moment regions is poured. This technique of using separate pours aims to minimize deck cracking over the piers. Most of the girder rotations at the bearings occur when the concrete in the positive zones is placed. We click the Name parameter and set the name as Deck Casting 1. We click the 3-dot icon button in the Pouring Stage parameter and select Select. In the interface that opens, we select Cast 1 Pour Stage. At this stage, the deck load and haunch load are calculated and applied on top of the non-composite girder. It is crucial to differentiate between the deck hardening stage and the non-composite state load applications. During finite element analysis, the self-weight of shell elements is computed and distributed to the nearest girders. Nonetheless, the haunch load is calculated in the library object and can be observed graphically in the FEA loading view. We click OK. We click the 3-dot icon button in the hardening stage parameter and select Select. In the interface that opens, we select Cast 1, 2, and 3 Gain Stiff Stage. During this stage, the deck, specifically the shell elements of the deck, gains stiffness and no load is applied. If no further loads are added during this stage, the results of the finite element analysis will remain unchanged because the sole modification is in the stiffness matrix. We click OK. We click the 3-dot icon button in the deck parameter and set Deck 1. We leave the start and end skew values at the default value of 0. The skew angle specifies the boundary of the deck pouring area, in addition to the start station under the Longitudinal tab. A skew value of 0 implies that the line defined is perpendicular to the alignment. A positive value rotates the perpendicular line clockwise, while a negative value rotates it counterclockwise. We also leave the haunch load parameter at the default ignore state. If the include option is selected, the haunch load is automatically computed and applied to the girder in the selected pouring stage. The calculation of the haunch load is based on the unit weight of the deck material, the selected taper parameter for the overhang region, and the haunch thickness. We click on the longitudinal category. We set the end station value to 111 feet. We also leave the parameters in the Transverse category as default. Typically, the deck pouring sequence does not require separating the pour in the transverse direction, and users can achieve this by selecting the Complete option. However, in some cases, such as rehabilitation projects, it may be necessary to separate the pour in this direction. In such cases, the Partial option can be selected. We return to the deck casting category. For other stages, we copy and paste the data from the Excel link provided in the video description. We click on the Longitudinal category and copy and paste the values here from Excel as well. We have completed the deck construction definitions. We click on the Superstructure Attachment construction object in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the barrier stage and click OK. Then we click the three-dot icon button in the Superstructure Attachment Elements parameter and select Pick. We select Barrier 1 and Barrier 2 from the screen and click Done. We leave the Self-Weight Factor parameter as default. We click the three-dot icon button in the Stiffness parameter. During staged construction analysis, bridge owners typically choose not to consider the stiffness of the barriers to be conservative and only take their weight into account. We select No for weight-only construction. We have completed the Superstructure Attachment construction definition. Since there are no concrete diaphragm, temporary support, or rail elements in our model, we will not define construction stages for these objects. If you wish to examine the construction stage definition of these objects, you can review the documentation whose link is shared. There is no deconstruction stage in our model. However, let us make a deconstruction definition to demonstrate how it works. To determine in which stage the deconstruction process will take place, we click on the construction stage object in the tree view. We define the deck deconstruction, girder deconstruction, cross-frame deconstruction, and substructure deconstruction stages respectively. We click on the deck deconstruction object under the Superstructure deconstruction category in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the deck deconstruction stage and click OK. We click the three-dot icon button in the deck parameter and select Deck 1. We leave the start and end skew values at the default value of 0. We click on the Longitudinal category and set the end station value to 50 feet. We click on the Transverse category. We click the three-dot icon button in the Transverse construction type parameter and select Partial. We set the left offset values to 5.5 feet and the right offset values to 20 feet. We click on the girder and bracing deconstruction object under the Superstructure deconstruction category in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Girder Deconstruction stage and click OK. We click the three-dot icon button in the Girders parameter and select Pick. We select Girder 2 from the screen and click Done. We click the three-dot icon button in the stage parameter again and select Select. In the interface that opens, we select the Cross-Frame Deconstruction stage and click OK. We click the three-dot icon button in the Cross-Frames parameter and select Pick. We select the first and second objects for Cross-Frame K-top and objects 1, 2, 26, and 27 for Cross-Frame X from the screen. Then click Done. After this process, we click on the Pile Deconstruction object under the Substructure Deconstruction category in the tree view. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Substructure Deconstruction stage and click OK. We click the three-dot icon button in the Substructures Above parameter and select Pick. We select Footing 1 from the screen and click Done. We perform the same process for foundation deconstruction. We remove our deconstruction definitions. Now let us define our loads. To be able to define stay-in-place load and future wearing load, we must first define a load geometry. Under the Loading category, we click on Load Geometry. We click on the quadrilateral object under the Surface subcategory. Surfaces with 4 sides can be defined in this section. We click the three-dot icon button in the Bridge parameter and set the bridge. We set the start station value to 0 feet, the end station value to 530 feet, and the surface width value to 36 feet. We have determined the geometry for which we will define the load. Now we click on the Surface Load object under the Static Load subcategory under the Loads category in the tree view. We will define 2 load definitions here. First, we will define the future wearing load. The future wearing surface load is a standard allowance in bridge design for repaving over the structure's lifespan. It is classified as a superimposed dead load. Standard design guidelines, such as AASHTO LRFD, generally recommend assuming an allowance of 25 to 35 pounds per square foot, which equates to roughly 2 to 3 inches of asphalt. We click the name parameter and set the name as future wearing load. We click the three-dot icon button in the surface parameter and set the surface we defined. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the future wearing stage and click OK. We set the value of 0.03 kips per square foot for the FZ parameter. Finally, we click the three-dot icon button in the element parameter and select Deck. Second, we will define the stay-in-place load. In bridge engineering, SIP refers to stay-in-place metal deck forms. The design SIP load is typically calculated as a dead load of 15 to 20 pounds per square foot, which accounts for the form's self-weight plus the extra concrete pooled in its corrugations. Stay-in-place forms are used to support wet concrete during deck construction. Because they remain in place permanently, engineers must account for their weight in the bridge's dead load calculations. Typical SIP load specifications, standard allowance. Many state departments of transportation, for example, Delaware and South Carolina, use a standard 15 to 16 pounds per square foot allowance for SIP forms. We click the name parameter and set the name as SIP load. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the SIP formwork stage and click OK. We set the value of 0.015 kips per square foot for the FZ parameter. Finally, we click the three-dot icon button in the element parameter and select Girder top flange. We have completed our surface load definitions. Now let us define our live load conditions. First, we click on the design lane object under the loads category. We will define AASHTO design lanes in our model. Design lane definitions can be created automatically in the OpenBrIM platform using built-in databases. We click the three-dot icon button in any parameter and click Import Design Lane. In the interface that opens, we select AASHTO Design Lane for database. We import the design lanes defined in the gravity, deflection, braking, and centrifugal categories in sequence into our model. We have completed our design lane definitions. Vehicle objects are also created automatically together with the defined databases. Now we click on the Influence Surface object under the Loads category. The effects of live load, braking load, and centrifugal load in OpenBrIM are calculated using the generated influence surfaces. The defined roadway is considered the boundary for applying live loads and is further utilized for influence surface definitions. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the live load stage and click OK. We click the three-dot icon button in the roadway parameter. The roadway geometry is utilized to establish the boundaries for the unit loads that are placed at equal spacing in both longitudinal and transverse directions. In the interface that opens, we set the roadway object defined in our model. We click the three-dot icon button in the live load category parameter. In the interface that opens, three options are offered to the user: gravity, braking, and centrifugal. When gravity is selected, the unit loads are applied in the vertical direction. In the case of braking, the unit loads are applied 6 feet above the deck level in the longitudinal direction along the alignment. For centrifugal or wind loads, the unit loads are applied in the transverse direction perpendicular to the alignment and 6 feet above the deck. When the user selects the centrifugal option, it is important to specify the highway design speed and centrifugal force factor under the centrifugal tab. The library component will calculate the radius of curvature of the traffic lane at each unit load station based on the alignment data and automatically compute the C factor in accordance with AASHTO 3.6.3.1. The unit load will then be multiplied by the C factor. Regarding how we determine in which direction centrifugal or braking unit loads will be placed, and whether the program automatically aligns and positions them correctly based on the alignment. Longitudinal and centrifugal are in the alignment coordinate system. Each unit load is placed with respect to the direction of the curve at that specific location. You can view all unit loads by selecting the loading mode and the influence surface you are interested in. Note that these loads are individually defined in the global coordinate system, while the combined load is perpendicular to the PGL. On the screen, an example of a centrifugal unit load applied perpendicular to the PGL and directed outward from the curve is shown. We set gravity. We leave the unit load spacing longitudinal and transverse parameters as default. The spacing of the unit loads in both longitudinal and transverse directions significantly affects the total analysis time. For each unit load, a finite element analysis must be conducted. For instance, if we consider a roadway that is 1,000 feet in the longitudinal direction and 50 feet in the transverse direction, using a spacing of 1 foot in both directions would require 50,000 finite element analysis runs. Additionally, identifying the critical vehicle positions using these runs would also be a time-consuming task. For this reason, when considering the longitudinal direction, it is recommended to use a spacing value of 10 feet, or the span length divided by 20 or 10, as it provides a good approximation. A good approximation for transverse spacing can be achieved by starting with a vehicle width of 6 feet and gradually reducing it to 3 feet in subsequent runs. To ensure that the model runs without any issues, it is convenient and faster to start with larger numbers for both longitudinal and transverse unit load spacing. For instance, using 20 feet in the longitudinal direction and 10 feet in the transverse direction can be a good starting point. Once you have confirmed that the model runs smoothly and have reviewed the design report, you can proceed with a spacing value of 10 feet in the longitudinal direction and 6 feet in the transverse direction to check your design. After finalizing your design, it is recommended to perform another check using a spacing of 5 to 10 feet in the longitudinal direction and 3 feet in the transverse direction. For other influence surfaces, we copy and paste the data from the Excel link provided in the video description. We click on the Live Load Case object in the tree view. We click the three-dot icon button in the Influence Surface parameter and select Gravity. We leave the maximum stress range parameter at the default value of No. If this is not a fatigue case, the maximum negative stress and maximum positive stress can be generated from different lane placements. However, when dealing with a fatigue case, a distinct methodology must be employed to calculate stress ranges from single lane placement. Please confirm by responding yes if this is a fatigue case. We click the three-dot icon button in the Multiple Presence Factor parameter and select Edit. Per AASHTO, the multiple presence factors are 1.2 for a single lane, 1 for 2 lanes, 0.85 for 3 lanes, and 0.65 for 4 lanes and more. For fatigue loads, use a single lane and select a multiple presence factor of 1 according to AASHTO 3.6.1.1.2. In the interface that opens, we set the values 1.2, 1, 0.85, and 0.65. We leave the maximum number of lanes parameter at its default value. If no limit is imposed, the maximum number of lanes that can be placed in the transverse direction is based on the dimensions of the roadway. For instance, A 55-foot roadway can accommodate up to 4 lanes, with each lane measuring 12 feet. Generally, there should be no limit, but in some cases, such as fatigue or permit loads, restrictions may apply even if the roadway geometry allows for it. For fatigue trucks, a single lane should be used, and it is important to set the maximum number of lanes to 1 per AASHTO. We click on the Design Lanes category. We click the three-dot icon button in the Design Lane Option 1 parameter and select Select. In the interface that opens, we select the HL93 design lane. For all live load cases, we copy and paste the data from the Excel link provided in the video description. We have completed our live load definitions. Now let us create our wind load definitions. We click on the wind load category under the loads category. Then we click on the AASHTO object under the wind load on structure subcategory. Wind on structure can be defined in 2 ways. First, according to AASHTO 3.8.1.2, wind load cases are generated after the user defines parameters in the wind on structure AASHTO section. The other way is that the WS graphical section can be used to make manual definitions for wind loads, allowing for different attack angles and constant pressure values. We click the three-dot icon button in the Stage parameter and select Select. In the interface that opens, we select the Wind Load on Structure stage and click OK. This component calculates the wind pressures for each structural element and applies the load in different directions in accordance with AASHTO 3.8.1.2. The nodal loads are then determined by converting the wind pressure values according to their respective tributary areas for different angles of attack. There are 9 cases: -60, -45, -30, -15, 0, 15, 30, 45, and 60. Computed for the right-to-left wind direction, and another 9 cases for the left-to-right wind direction, totaling 18 cases. Envelopes for these 18 cases are automatically generated separately for the Strength 3, Strength 5, Service 1, and Service 4 limit states. We leave the span height variation parameter as default. The span height variation parameter is defined as follows. The computed pressure values are a function of the structural heights, as specified in AASHTO 3.8.1.2, which states that in the case of a long multi-span bridge with a significant variation in the ground surface elevation beneath the bridge, such as a bridge crossing a valley, the structure height may vary from span to span. For each span, the structure height can be taken as the largest value in the span. If the user wishes to enter different structural heights for various spans, they should select Yes for this parameter. In most bridges, it is not necessary to enter different structural heights for various spans, so selecting Yes for this parameter is not required. We click the three-dot icon button in the Structural Objects and Pressure Parameters and select Edit. We click the three-dot icon button in the Applied Elements parameter and select Pick. Typically, exterior girders, barriers, deck, pier caps, and end bends are chosen as the elements to which the wind load is applied. We select Barrier 1. We click the three-dot icon button in the Wind Direction parameter. Choose the right-to-left direction for barriers or exterior girders located on the right when looking up station from the alignment. In contrast, select the left-to-right direction for left barriers and exterior girders. For the deck and substructure elements, select both directions as the wind direction. We set the left-to-right option for Barrier 1. We click the Structural Height from Ground Line parameter. According to AASHTO 3.8.1.2.1, the structure height parameter is utilized in the computation of Kz, the elevation coefficient. According to AASHTO, In no case shall the structure height used in calculating KZ be taken less than 33 feet. According to the AASHTO table below, if the user enters a structural height of less than 33 feet, the library object will utilize KZ values of 0.71, 1, and 1.15 for B, C, or D categories. We set 52 feet for barrier 1. We leave the gust effect factor strength 3 and service 4 parameter at the default value of 1. The gust effect factor is determined using a structure-specific study, or as specified in AASHTO Table 3.8.1.2.1.1 for strength 3 and service 4 load combinations, and 1 for other load combinations. The gust effect factor may vary for different state specifications. We also leave the gust effect factor strength 5 and service 1 parameter at the default value of 1. For strength 5 and service 1 load combinations, this parameter should be set to 1.00 as per AASHTO. We also leave the drag coefficient parameter at the default value of 1.3. The drag coefficient is determined using a structure-specific study or as specified in Table 3.8.1.2.1.2. The drag coefficient may vary for different state specifications. For other applied elements, we copy and paste the data from the Excel link provided in the video description. We exit the interface with the back button. We maintain the strength 3 design wind speed parameter at its default value. The user specifies the design wind speed for the strength 3 limit state, while the wind speeds for the other limit states are calculated in accordance with AASHTO Table 3.8.1.1.2.1, as shown on the screen. We have completed the wind load on structure definition. Now we click on the Lane Positions object under the Wind Load on Live Load category in the tree view. To define wind loads for live loads, several parameters must be established, including lane positions. These lane positions will be utilized in the sections for Wind on Live Load AASHTO and Wind on Live Load Custom. This section allows users to specify the relevant lane positions. We click the three-dot icon button in the bridge parameter and set the bridge object. We set the end station value to 530 feet and the transverse offset to -11 feet. We repeat the same process for transverse offset values of 0 feet and 11 feet. We click on the AASHTO object in the tree view. If the user wishes to apply static wind on live load, they can utilize this option. The line load shall be applied onto the central line of the lane position designated by the user. In the Wind on Live Load AASHTO section, users can choose defined lane positions. The line load will then be applied to these positions separately. For each designated lane location, a unique result scenario will be generated. The critical envelopes of these result scenarios will be used in subsequent design procedures. We click the three-dot icon button in the center lines of lanes parameter and select Select. In the interface that opens, we select the lines we defined and click the Add button. We click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the Wind on Live Load stage and click OK. We leave the transverse force value as default. Enter the transverse component values here as per AASHTO Table 3.8.1.3.1. The default value is 0.1 kips per linear foot. If the user inputs a different value, the factors listed in the table will be employed to calculate the remaining angles. For instance, if the user inputs 0.2 kips per linear foot, the transverse component for a 15-degree angle will be computed as 0.2 multiplied by 0.088. We have completed the Wind on Live Load definition as well. Finally, we click on the Uniform Temperature Load object under the Temperature Load category. Normally, two distinct scenarios should be generated, with two stages for contraction and expansion. We click the name parameter and set the name as TU expansion. We click the three-dot icon button in the bridge object and set the bridge object. Then, we click the three-dot icon button in the stage parameter and select Select. In the interface that opens, we select the temperature expansion stage and click OK. We click the temperature change from mean parameter. When dealing with expansion, it is necessary to input a positive temperature value, whereas a negative temperature value should be utilized for contraction. We set the value of 40 Fahrenheit degrees for our model. We repeat the same process for temperature load contraction. Together with the temperature load, we have defined all loads in our model. Now let us review our construction stage and load definitions in the FEA model on the screen. We select the loading option from the menu. We set the scale value to 128 and review our load definitions by navigating through the stages. We click the Analyze button. After the analysis is completed, we close the interface by clicking the Close button. We activate the Deformed button in place of the Loading button. We review the deformed state by navigating through the stages. We click on Line Forces. We select Substructure stage as the construction stage and view the axial load on the screen. We activate Composite forces. In the interface that opens, we click Select Value. We select G1 Composite Forces and click the Show button. We adjust our FX option to FZ. On the screen, we see the FZ results generated in the girder stage. Then, we adjust the FZ option to MY. By changing the stages, we can observe the MY result changes. We set the composite force option back to model. Then we set the stage option to Live Load HL93. Finally, in the FEA section of the spreadsheet, we click on Node Reactions under the Results category. In the spreadsheet, we view the node reactions results for the live load case. Here, by clicking on any node reaction result, we can view the corresponding vehicle position in the FEA model. We can perform the same process for composite element forces as well. We have completed defining the staged construction model in our project.